Thank the organizing committee for inviting me to give a lecture on planetary outer atmospheres, interfaces from atmospheres to magnetospheres. As the lecturer following me, Steve Boulder, will be focusing on the terrestrial planets, I'm going to focus here on the outer planets. So, okay. Yes. Okay. So first of all, we can ask ourselves, why should we care about the outer planets, Jupiter, Saturn, Uranus, and Neptune? Well, they are interesting by themselves. As Fran mentioned this morning, that their moons, I mean, they have, Jupiter are more than 60 moons, are for most of them within the magnetosphere, and there are some very active. They interact with their planet. Some are very interesting also on an astrobiological point of view, so active. For instance, I'm thinking of Io around Jupiter, or Enceladus around Saturn. For an astrobiological point of view, I'm thinking of the icy moons and on Titan. So they have mini systems who are of very, which are of great interest. In addition, the past decade, we have been discovering exoplanet, primarily a very massive exoplanet, similar, in terms of mass of Jupiter, mainly due to observational bias. And so that's really important to be able to put those exoplanets into context and contrast them with the outer planets in our solar system, those outer planets that we can examine in situ. Okay, so here's the outline of my presentation, my lecture. First, I will be setting the scene. I will be, so I'm focusing on the outer layer, thermosphere, exosphere, ionosphere. What are those layers? I will start by defining them. And then what are the energy sources which are absorbing those layers? Then I will be focusing on the ionosphere of the giant planets and how they are produced and what are their characteristics. And that will conclude the first lecture. For the second lecture, I will I will focus on the auroral emission, and which help to get to illustrate the, infer information on the magnetosphere, ionosphere, thermosphere system, and the coupling between those different regions. In particular, I will focus on the effect on the magnetospheric forcing on the ionosphere, thermosphere system, and on the energy crisis of the giant planet. And finally, I will mention future prospect. Okay. So first, let's be setting the scene. So I'm focusing on the outer planet, Jupiter, Saturn, Uranus, and Neptune, which have an atmosphere primarily made of hydrogen and helium. They have been visited by many spacecraft through flybys, Pioneer 10, 11, Voyager 1, 2, Ulysses, and Cassini as for Jupiter. And also by orbiter, Galileo for Jupiter, and Cassini-Huygens for Saturn, which has been orbiting Saturn since 2004 and still orbiting Saturn, and expected to do so until 2017, when it will disintegrate into its atmosphere. So what is presented here is a profile in pressure of the temperature in the atmosphere of Saturn, Jupiter, and Earth. And you can see that the different regions, troposphere, stratosphere, mesosphere, thermosphere, and exosphere, are associated with a different temperature gradient. So we're going to focus here on the thermosphere, which is associated with a positive temperature gradient. So the energy sources are depositing in this outer layer. And the exosphere, where actually the temperature is more or less constant, and we refer to the exospheric temperature. So that's the typical temperature in this region. So constant temperature. We'll come back on that later on. So the upper atmosphere are gravitational bond. I mean the molecules, the atmospheric atoms and molecules are bound to the planet gravitationally. It's a key transition region between the lower atmosphere and the space environment, especially the magnetosphere in the case of the outer planet. And the energy and momentum sources, so I mentioned it's a positive temperature gradient because of the absorption of solar radiation, more specifically extreme ultraviolet and far ultraviolet, so spreading from 10 to 100 nanometer. Also, energetic particles from planetary magnetosphere are absorbed in this region, and also from forcing from below. For instance, a gravity wave are can break into the upper atmosphere, which is another source of energy and momentum. Because extreme ultraviolet, I mean, those two other energy sources vary greatly from one body to another, but extreme ultraviolet is, I mean, all planets in the solar system are reached by the solar radiation. And extreme ultraviolet is absorbed by any species, any atoms, any molecules. So it means that there will be then a thermosphere in all bodies which has an atmosphere. Let's look at the composition. Here's the profile and altitude of the number density at Saturn. Before to continue, we are dealing with outer planets, so they are gaseous planets. There is no hard surface. And so the reference altitude is usually taken as 1 bar level by analogy with the Earth. So, as I mentioned, here's a number density as a function of altitude, and here pressure. And you have mainly two regions. You have the homosphere here and the heterosphere. In the homosphere, you have a convective mixing. So the major neutral species have a constant mixing ratio. The abundance is independent of altitude. You find also very heavy constituents, especially hydrocarbons. When you go higher up in altitude, then there is much less mixing, and what's the physical process which is taking over is molecular diffusion. So it's going to have, they're going to be diffusive separation between the species. So what does it mean? It means that the heavier a species is, the faster its number density going to decrease with increasing altitude. So the heavy species like methane, their number density is going to fall very, very quickly because it's heavy. While, however, helium, H and H2 are going to fall much less. So it means that as a result, the heavy species are going to be confined below the homopause, and above in the heterosphere, you will have many hydrogen, H2 and helium. As a result, if those species are ionized, then you will have a relatively neutral chemistry, unlike what you will encounter below the homopause. So speaking of ionization, so the ionosphere, what is it? It's the ionized part of the upper atmosphere. Again, it's present at any planet which has an atmosphere. As we will see later on, extreme ultraviolet have enough energy to ionize. And I mentioned earlier, extreme ultraviolet solar radiation is absorbed by any constituent. Unlike, for instance, in the MUV or in the infrared, not all species are absorbent. In the extreme ultraviolet, all species, at least for part of the spectral range, they are absorbed. So it's a key conducting, it is a conducting layer, and it's a key layer for coupling the atmosphere with the magnetosphere. In particular, it helps it ensures the closure of the magnetospheric current system. It's also a key source of heating of the high latitude upper atmosphere, and I will come back on that during the second lecture. Okay, so I said part is ionized, but is it fully ionized, partially ionized? It's illustrated here. Here's a profile and altitude of the number density for the neutral, and here for the ion. You don't need to look at the details of which ions. That's the point here is that it's the same scale on the x-axis for both figures. So it means that the electron density and the major ion species have the electron density and major ion density is about of the order of 10 to the 4, 10 to the 5 per cubic centimeter, meaning in this region, which is order of magnitude below the density of the main neutral. So they are minor species. Ionospheric species are minor species. Though they are minor, they play a really key role, as we will see, in the ionosphere, thermosphere, magnetosphere coupling. Fran has shown that this figure earlier. Here I just wanted to say we have plasma, so they will be influenced by magnetic field, and I wanted to focus on just two extreme cases: Saturn, for which the rotation axis is parallel to the magnetic moment axis, while for Uranus the angle is almost 60 degrees. Uranus, the lying planet, with the rotation axis close to the orbital axis. So that makes a quite complex configuration of the magnetic field and the coupling between the ionosphere, thermosphere, and the magnetosphere. So I've spoken about solar radiation. I've spoken about energetic particle, and their deposition in the atmosphere will yield different processes, and in particular the formation of an ionosphere. So let's look at those different processes. So here's solar photon, and they can be absorbed by atmospheric species that will yield, for instance, ionization. And because of the difference in mass between the ion and the electron, then if there is any remaining energy, it will go to this photoelectron, which will then belong to the suprathermal electron population. You can have also dissociation, excitation, which may yield then to air glow emission. As for the suprathermal electron, which can be photoelectron, which can be auroral energetic particle coming from the space environment, or secondary electron induced by electron impact ionization, they can interact with the neutral species, yielding excitation and ultimately, directly or indirectly, auroral emission if the original source is auroral energetic particle, or air glow if the original energy source was solar radiation. They can also ionize further. They can also, through Coulomb collision, interact with the thermal electron, yielding a heating of the ionospheric electron population. And that is just the first step into the energy deposition. After you will have a reaction, you will have the momentum and energy balance will be perturbed by this energy deposition, and will drive the characteristic into the upper atmosphere. We have heard this morning the strong coupling between the magnetosphere and ionosphere at high latitude, and I will focus on that on the second lecture. But for this lecture, the question I would like to address are: how well is a vertical and latitudinal ionospheric structure captured, and can we explain it? Can we model it, what we observe? And is there any atmosphere-magnetosphere link at low and mid latitude? Because we always think about high latitude, but what about low latitude? So first, the ionization sources, and then we will look into losses, and then the electron density per se. So typical ionization potential, what the amount of energy you need to strip a molecule of an electron, is typically 13 eV, which corresponds in terms of wavelength for solar radiation at 100 nanometer. So solar UV radiation, I mean, from 1 to 10 is more soft X-ray, and 10 to 100 EUV radiation will have enough energy to ionize neutral species. Just a reminder, the solar flux decreases by a square of the distance from the sun to the planet. So the further away you will be, the smaller the solar flux will be. Another source of ionization is energetic particle from the space environment. For the outer planet, that will be from the planetary magnetosphere, and which with energy which spreads from a few keV to a few hundreds of keV. So far, you have been very silent. Is it trivial, or don't hesitate to ask questions if needed. Yes, it's after lunch. Okay. So now, what I would like to look at is I've mentioned those two ionization sources. What is the relative importance of each of them? I show that in this table for the outer planets along with the Earth. So for Earth, clearly the solar EUV input is dominant compared with the auroral input. Jupiter, with this very strong magnetosphere, Fran really make a point this morning about it, then the auroral input is significantly larger compared with the solar EUV. It's also true at Saturn and Uranus, though the ratio is not as strong. But and then at Neptune, it's very complex also magnetosphere, makes it not very efficient, and as a result, the solar EUV input seems to be dominant, though you are so far away from the Sun. Some of you may have said, well, Jupiter is further away from the Sun than the Earth. How on Earth can the solar EUV input be larger? It's just that it's the total solar input integrated over the planet. The surface is larger, okay? But per square meter, it is smaller. Just want to clarify. Yeah, yeah.
On the last slide, why is the auroral Uranus larger?
Well, you know, you have this very large angle, both at Uranus and Neptune. And the magnetosphere, ionosphere, the magnetospheric input onto the atmosphere is quite complex and very variable. And actually for Uranus, we will see later on that it can be very large, but it can be also quite smaller. And that is because of the configuration. And for Neptune, it seems that it's not as efficient, the magnetosphere, but again, it's because it's quite atypical due to the large angle between the rotation axis and the magnetic dipole axis, or magnetic moment axis. Yes, yes. Sorry.
Go back to your previous
yes.
point you were making. I'm wondering if Uranus and Neptune, we really know that those are 10 gigawatts plus or minus a factor of 10 each. I mean, do we? I mean, I don't want to.
Okay. Yeah. No, they are very large. No, I agree. There are very large uncertainties on those numbers. I agree with that. No, but it's true. I mean, those numbers were from 2002, and the recent infrared radiation, infrared observation have shown that we don't actually understand very well the Uranus system, and so at times it's very large, but it's very variable. Thank you for pointing it out. So before to look into how those energy ionizing sources deposit their energy in the upper atmosphere, I would like to make a pause and point out that in the ionosphere, in the outer layer of a planet, you have two populations of electrons. You have on the one hand suprathermal electrons, which can be photoelectrons, which can be electron from the space environment, which can be secondary electron produced by electron impact ionization. And on the other hand, you have the thermal electron and ion. Those electrons which are produced, ultimately they are going to, through collision, being thermalized. And so you end up with a thermal electron and ion population. The bulk of the ionospheric population is this population, is the thermal electron and ion. It undergoes a lot of collision with the neutral primarily, and so their energy distribution is well described by Maxwell-Boltzmann distribution. And this population, however, it represents a very, very small part of the bulk of the ionospheric population. It's just the tail of the distribution. However, they undergo collision through the atmosphere, and the probability of losing energy varies with their energy. As a result, you can't make any assumption on their energy distribution. You need to calculate it explicitly. So the way you treat those two populations is very different. So on the one hand, you can describe the thermal population in terms of macroscopic quantities, because you know the energy distribution. You can describe it in terms of just position and time, and describe it in terms of macroscopic quantities such that the number density, the bulk velocity, and the temperature. You can define a temperature to start with. On the other hand, the suprathermal electron, which represent a very small part of the population, but which is key because it's the source of ionization, of excitation, of dissociation, and of thermal electron heating, needs to be treated in a kinetic way and to be described with macroscopic quantity, meaning physical quantity which are a function of not only position and time, but also velocity. So you need to define the quantity which describe them in the phase space. And for that, you will solve the Boltzmann equation, which allow then to calculate the particle intensity as a function of energy, as a function of altitude, and from that you can derive then electron production rate, heating rate, excitation rate, and so forth. So you have those two populations. One is very minor in terms of number, but play a key role and is actually the source of the second one, of the ionospheric thermal population. So let's go back to the two sources. And I think that Carol showed you similar spectra earlier. So one of the source of the ionosphere is solar radiation. So here's the spectral radiance as a function of wavelengths from the UV visible to the infrared. And you see here the black body radiation associated with the temperature of the photosphere. And in the visible and infrared is a pretty good approximation of the spectral radiation, which is here valid at 1 AU on the top of the atmosphere before absorption in the atmosphere. Here you can see part of the black body, but actually associated with the bottom of the chromosphere, the colder part of the chromosphere. And finally, but here, 100 EVs here. I said ionizing radiation is below 100 nanometer. So we're actually interested in this range, which is highly structured and departs strongly from the black body radiation. In addition, also, what is shown here is the 11-year cycle ratio as a function, again, of wavelength. And though overall the variation is not more than 0.1%, in, again, the extreme ultraviolet, it's more than 100%. So solar variability, solar cycle will strongly influence the ionosphere. And again, I think that Carol has introduced you with the spectral flux is shown here as a function of wavelength, and all those lines which are associated, which are produced in the chromosphere or transition region, and finally for the most energetic one in the corona, very hot part of around the sun. I just wanted to point out the strongest in the extreme ultraviolet, the helium-2 at 30.4 nanometer, which will be driving many of the, all of the ionosphere and ionospheric peak. So we have the solar radiation, and so you have photons, and on the other hand, I spoke about suprathermal electrons, which can be auroral electron or photoelectrons. Now, there is a fundamental difference between on the one hand, the absorption of solar radiation, and on the other hand, the energy degradation of suprathermal electron. And so I would like to make a quick poll here, if I'm going to manage to do it. I'm pushing. Come on. It's up. You have it? Oh, okay, great. So the question is, the more energetic a solar photon, the deeper it is most likely to be absorbed in the atmosphere. If you agree, you push yes. If you don't agree, if you disagree, you push no. All of you have? Done? So result? Ah, that's great. It's 50-50. So I'm glad that I have actually the following up slides. It means that at least for 50% of the students, it's work. Sorry? Ah, yes, I'm sorry. Yes, you told me about it. Yes, 50-50. I'm astonished, but okay, so that was actually good to do the poll. So let me go back to the presentation. And the main point of the following slides is to actually answer to this. And hopefully then I can do it later on and it will be 100% on the correct answer. So I will not answer to you, sorry. I'm new to nice meeting, so. Okay, so the fundamental difference is that here a solar photon, if they don't undergo any scattering, if they are absorbed and the end of it, which is a good approximation in the extreme ultraviolet, then you have the energy of the photon and at some point it's absorbed and it's the end of it. On the other hand, the suprathermal electrons, they start with a certain energy and they will undergo collision throughout the atmosphere and lose a bit of energy at each collision. And so ultimately, they will be thermalized, so meaning they will reach a tenth of an EV. And so for an electron, for a suprathermal electron, the more energy it has, the more collision it needs to undergo to be able to be thermalized, because all of them needs to reach the thermal energy, which is, for instance, sorry. So for the suprathermal electrons, for photoelectrons is tens of eV to 100, 200 eV. For the auroral electrons is a few keV to a few hundreds of keV, depending on where you are. At Earth and Saturn, it will be more on the keV side. At Jupiter, 100 keV. But if you have 1 keV, then if you assume that the electron doesn't undergo any redistribution in angle, then if it goes straight down, just for simplification, then it will undergo a certain number of collisions to reach a tenth of an EV, which is the temperature of the thermal electron. Now, if you take 10 keV, obviously it will need to undergo more collision to reach the 10th EV. So it means that if it goes straight, then it will be thermalized lower down. For a photon, it's not the case. So what happened? Well, in the extreme ultraviolet, if we can assume that the radiation primarily is extended, it only primarily undergo extinction, I'm going to say it, meaning that you can neglect scattering into the beam or emission in the atmosphere. Then you can apply the Lambert-Beer law, and the attenuated solar flux at a given altitude in the atmosphere and at a given wavelength is given by the solar flux at the top of the atmosphere, that wavelength, times exponential minus the optical depth. And the optical depth is a function of the photoabsorption cross-section associated with the neutral N, one of the atmospheric species, and at the wavelength lambda. You can see it as the probability, similar to a probability of absorption. And it's expressed in a surface unit, so you can see it like the surface of conceptually a target. The larger the target, the bigger the chance that the photons is going to be absorbed. And then you need to know also how many absorber you have, and here is the column of absorber along the radiation path, function of the solar zenith angle. So in the extreme ultraviolet, I've mentioned that all neutral atom and molecule are absorbing, so you consider all the neutral species. But how is the photoabsorption cross-section? Well, it can be highly structured. So you can have, at a given wavelength, given value of the photoabsorption cross-section, and at higher energy, a photoabsorption which is higher or smaller. So a priori, you will not know, I mean, you can't say the more energetic a photon, the deeper in the atmosphere it's going to be absorbed. It all depends on what are the absorber at that wavelength. Well, in the ultraviolet, that will be most of, I mean, all of them, up to a certain point, up to the ionization potential, and at least for atoms. And then what is the photoabsorption cross-section? And that really is highly structured. I will skip the photoelectron production rate just to illustrate here. What is shown here is pressure, altitude, and wavelength. And the line here is that correspond to the altitude or the pressure where the optical depth equal 1. For atmosphere in hydrostatic equilibrium, it corresponds to the altitude or the pressure where the solar photons at a given wavelength are going to be absorbed. So you can have photons which are a lot less energetic, higher wavelength, than some other, and they're going to be absorbed at the same altitude. All depends on the photoabsorption cross-section and the absorber. So the answer was no. I've focused on the absorption of solar radiation. What about auroral electron, I mean suprathermal electron coming from the space environment? Here's a profile and altitude of the electron production rate, and each color corresponds to a different mean energy for the incident electron at the top of the atmosphere. And for them, as I mentioned earlier, the more energetic they are, the more collision you need to have them undergone in order that they are thermalized. So the larger, so from this curve to this curve, the mean energy is increasing, and then the deposition, and therefore the electron production rate peaks at a lower and lower altitude. And that just for reference, the electron production rate, we calculated from the attenuated electron, the electron intensity, which is function of the energy and altitude, energy of the suprathermal electron and altitude, probability of ionization, that's the suprathermal electron ionize a neutral N at a given energy. And overall, it's proportional to this quantity's electron production rate to the energy flux associated with those energetic electrons at the top of the atmosphere. So, but how does it compare? Solar versus auroral for the electron production rate. Here it's an example for Saturn, where at high latitude, so it means that solar illumination is not as intense at the equator. Here's the profile and in altitude of the electron production rate. Here in dashed line is the photoionization. In solid line is the electron impact ionization associated with photoelectron and their secondaries. In green, that's for soft electron. I mean, look, the energy flux is very small, 0.03 milliwatt per square meter. Still, they are order of magnitude larger than the solar-driven electron production rate. And then in blue, the hard component, 0.1 milliwatt per square meter. And here it's still order of magnitude even more compared with the solar deposition. So it gives you a comparison between the solar-driven versus the auroral at high latitude. Okay, so we are focused on the production. Well, we would like to know how many electrons we have. For that, we need to take into account the loss of electron, and we need to take into account transport. So because it's thermal, I say that the thermal population, we can describe it because they are thermal, we can describe it in terms of macroscopic quantities. So we can use the conservation equation, the continuity equation, to calculate the number density. And you need to take into account production, So we just discussed production due to solar and auroral ionization, loss through chemical reaction, and also variation due to transport due to neutral wind or diffusion. So let's first look at loss of ion, chemical loss. So for first atomic ion, an atomic ion could recombine with an electron and radiatively, but such a reaction is extremely slow. What happens is that there is actually ion-atom interchange, and then the atomic ion react with a neutral, yielding the production of a molecular ion, and that's the main loss of ion in atomic ion in the atmosphere. As for molecular ion, well, they can also react through ion-neutral reaction. But if you look at the terminal molecular ion, terminal that after that there is no longer an ion, but you have only neutral product. That's done through that happens through a dissociative recombination between the molecular ion and the electron, yielding a neutral product. And I would like just to mention, because we're going to use it just after, that if there is one dominant ion, okay, one step back. Here, the loss rate for the XY plus molecular ion is given by the reaction rate associated with this reaction times the number density of the reactant. But if you have many one ion, dominant ion, then its density is going to be equal to the electron density. And so it means that those two quantities are equal. And so the loss is given by the recombination coefficient. So the reaction rate associated with this reaction times the electron density to the square. And under photochemical equilibrium, where the transport term can be neglected, and if you can neglect also this term, assuming so stationarity, the continuity equation is reduced to production equal loss. And if you have many one ion, it means that production of the ion will be equal to the recombination coefficient times the electron density to the square. It means that it's very easy then to calculate the electron density as a function of the ion production rate. Now, where photochemical equilibrium occurs, I'm not going to go into details. I just put it those timescales for reference. But you have to compare the chemical timescale with the transport loss timescale associated with diffusion or neutral wind. And one result for Saturn, it's illustrated here, profile and altitude of the timescale. And here's the chemical timescale, here's the diffusion timescale, and here is the timescale associated with neutral wind for different values of the neutral wind. And you can see that timescale are the smallest timescale in the deep ionosphere above the homopause is associated with chemical timescale. So the main loss is through chemistry, chemical reaction. So you can assume photochemical equilibrium in this region. However, higher up, diffusion timescale are much smaller than chemical timescale. So it means that diffusion will be a dominating process, and you need to take this process into account. So it's really good to estimate timescale such that you know what is a dominating process, and in between, of course, both processes will need to be taken into account. Well, now we have all the ingredients to be able to estimate the electron density. So we have in the giant planet H2. So what is the ion that's going to be produced through photoionization mainly? Yeah, H2 plus. But actually the major ion which are observed are H plus and H3 plus. H2 plus react very quickly with H2, leading to the production of H3 plus. And H3 plus is usually the terminal ion, and then recombining with electron, yielding a neutral product. H2 can be also ionized through dissociative ionization, yielding the production of H plus, and H plus is the long-lived ion. But if you consider just those reactions and stop there, the estimate of the electron density is significantly larger than what is observed. So we need a loss process. There have been different ones which has been invoked in model, but one is a charge exchange reaction where a long-lived ion, H+, react with H2 at a vibrational level equal or larger than 4 and yield H2+, which we saw from above will react quickly and become H3+, and H3+ is a shorter-lived ion. So you start with a long-lived ion and you transform it in a short-lived ion, and as a result you will have a decrease in electron density. So the more H2 in vibrational level you have, the larger the reaction rate will be, and the more you will have a conversion of the long-lived H+ ion into H3+, a shorter-lived ion, and then you will have a decrease in ionospheric densities. I am short in time, so I will move on here. Here's the latitudinal structure. So that's a total electron content, which is the electron density integrated over altitude, which is shown here as a function of latitude. At the equator, strong solar illumination, and it decreases as you go towards higher latitude. So if you neglect auroral precipitation at high latitude, the first thought would be, well, the electron density is going to be the largest at the equator and will decrease with increasing latitude. Exactly the opposite than what we observed using the Cassini radio science subsystem. So what's going on? What do you think? Sorry? Yes. So there is water at low latitude. And what's water doing? Well, H+ is going to react with water, H3+ as well. And so in the first reaction, you will have then H2O+ produce. And H2O+ is a very short-lived ion, and then will convert into H3O+. And H3+ also interacting with water will yield H3O+, which is shorter-lived than H3+. So you go from longer or mid-lived ion to shorter-lived ion, again a decrease in electron density. And in that case, the terminal ion is no longer H3+, but actually H3O+, which is shorter-lived, so decrease in electron density. But you told us that we will be speaking a bit of the magnetosphere. So recently, this year, there was a study looking at the intensity of H3+ emission as a function of planetocentric latitude, looking at two different wavelengths. Each black curve represents a different wavelength, 3.9 and 3.6. Oops, micrometer. Sorry, that's micro. And you can see that there is some increase sometimes. And here, for instance, this increase corresponds to the location of the Cassini division. So when you have less inflow, then there is less decrease in electron density. So what is precipitating is not actually H2O, but it's water ion. So primarily H2O+. And H2O+ will react with H2, and that will lead to H3O+. H3O+ will recombine, yield to H2O and OH. OH can interact with H2, yielding to H2O. So you produce a lot of water in situ, and that then, well, we just saw on the previous slides what happened when you have a lot of water in situ. H+ and H3+ will be converted into H3O+, which is a shorter-lived ion. But in the Cassini division, where you have a whole or less dense water, or the rings are, there is a gap, then there will be less water ion flow, and that means that the decrease will be less, and you will have a peak in the electron density. Last point I would like to make is about the altitude structure, vertical structure. Here's the profile in altitude of the electron density from Galileo, from Voyager, and here from Cassini. Well, it's structured. You have a very complex structure and spaghetti-like. Can we capture it? Here's the altitude, again, as a function of electron density. In gray, radio science experiment from Cassini, and what one of the different model would provide. In terms of peak, well, you are in the ballpark. In terms of structure, we are light years away. So what's going on? I've so far focused primarily on the forcing from above, but you have also forcing from below. I mentioned the upper atmosphere is a transition region. And so it interacts with the space environment above and also from the atmosphere below it. Okay. Yes. And here are simulation when you take into account gravity waves which break into the atmosphere. An example here at Jupiter and two examples here at Saturn. Here the blue line is the observed structure. The black line is what you would the model predict if there is no gravity wave breaking through, and in red the gravity wave breaking through. So the influence of the gravity wave on the electron density. So there is a clear coupling also, not only from above but also from below. So the take-home message for this lecture. The ionization sources are the extreme ultraviolet and soft X-ray, solar radiation, and magnetospheric energetic particles. I spoke only about electrons, but you have also protons and ions. Photoabsorption versus particle deposition. So if there is one thing that I would like you to remember is that the absorption of solar photons varies, depends on the photoabsorption cross-section and on the absorber. So in the ultraviolet, okay, in extreme ultraviolet, all molecule atoms absorb, but the photoabsorption cross-section can be highly structured. So it can be higher or lower and varies as a function of wavelength. So a priori, you cannot say photoabsorption, the photons, because it's more energetic, is going to be absorbed lower. MUV, infrared radiation, penetrates lower down because there is less absorber. And so the key thing is photoabsorption values and what are the absorber. Okay, ionospheric composition. Usually what you encounter in the solar system, and I'm sure Steve will also mention it later on, you photoionize, the atmospheric species are photoionized, but the ions which are produced are usually very reactive, and the major ions that are observed are usually not those which are photoionized, but like you have H2, it's photoionization, you produce H2+, the one major ion in the deep ionosphere is H3+. And that, you find that throughout the solar system. So you need to take into account chemistry. Even if it's simple one, still, it needs to be taken into account. Ionospheric density, I have not discussed in length on that, but it's very sensitive to the amount of H2 vibrational, of ion drift, on water inflow, which are not very well constrained. So there are large uncertainty in our estimate of the electron density. As for the vertical and the latitudinal structure, there is a clear ring contribution to the latitudinal and also vertical. I didn't highlight it, but also vertical structure. And the atmospheric gravity wave seems to strongly contribute to the vertical structure, and there are one strong candidate to be able to explain the very complex vertical structure that we observe. So thank you very much. If you have questions for this first lecture.